So, good evening, everyone, and welcome to the third session of live problem solving on fundamentals of electronic device fabrication. So, last week, people had asked me some doubts regarding the fluxes that is associated with the oxidation process. So, can you please once again confirm that my screen is visible and I'm audible to you as well?
Yes.
Okay. So basically, what was asked last day was, so suppose in the oxidation process, like there are two cases. One is a rate limited step and one is a reaction limited case, right? So in either cases, how do you like solve this particular equations? So for that, we need to consider the oxide growth model as shown in particular figure. So first I'll draw the figure. We are considering two interfaces. So this is a gas phase. This is the oxide layer that has already been formed, and this is the bulk of the silicon. So let us assume that the concentration of the oxidation species here is Cg, and on the surface let it be Cs. So we are considering a thicker surface, and here let us assume that the concentration is C0. And at the interface of the oxide layer and the bulk silicon, we have a concentration of Ci. So basically it goes from Cg to Cs, and then from Z0 to Ci. So these are the three cases. And now in every oxidation process, three fluxes will be associated. So can anybody remember from last class and tell me what those three fluxes were? Hello, am I audible? Yeah, can you just, somebody can you please memorize from last class and tell me what were the three fluxes associated with every oxidation process? Okay. Is it better now?
Yeah.
Okay. So as I was saying, can anybody please remember from the previous class and let me know what were the three fluxes that were associated with the oxidation process? Yeah. So basically in every oxidation process, three fluxes will be there. First, it will be F1. F1 corresponds to the transport of oxidizing species from the bulk of the gas phase to the surface of the oxide layer. So this will be F1, right? So that is the bulk of the gas phase to the surface of the oxide layer. Next is F2. It corresponds to the transport of oxidizing species through the oxide layer to the oxide silicon interface. So that will be the second flux, F2. This is F2. And finally, we have F3. That is the reaction of oxidizing species to form the new oxide layer. So this will be F3. And in steady state, what will be the equation? In steady state, we can say that F1 is equal to F2 is equal to F3. So, and now we need to find the equations of expansion for F1, F2 and F3. And then upon solving, we will get the conditions for reaction control and diffusion control oxidation. Is that clear till now? So first is F1. That is, what was the flux F1? transport of oxidizing species from the gaseous phase to the surface of the oxide layer. This can be given in terms of a simple mass transport equation. It is given by Hg into Eg minus Cs, where Cg is the concentration in the gaseous phase and Cs is the concentration in the surface. So Hg here is the mass transfer coefficient in the gas phase. Now we will be rewriting this equation in terms of C star. So we'll write as H into C star minus C0. So what is C star and C0 here? Can anybody tell me? Do you remember from the last class? So C star is basically what? Equilibrium bulk concentration. Equilibrium bulk concentration of the oxidizing species within the oxide. So basically C star is the equilibrium bulk concentration of oxidizing species within the oxide. And one more assumption that we are taking here is that once the oxide layer is formed, there is no dissociation taking place. And Z0, if we remember here, we can say that it is the concentration on the interface between the gaseous phase and the oxide layer. And H is related to Hg as H is equal to Hg by H Kb into T. This relation will be getting using Henry's law. So now we have the equation for F1. So now we are talking about F2. F2 means diffusion of the oxidizing species through the oxide layer, right? So similar to Fick's law, we will be having an equation, D into C0 minus Ci by D0, where D is the diffusion coefficient, C0 and Ci are the concentration of oxidizing species on the either interfaces, and D0 is the thickness of the oxide layer. And the equation for D, as we have discussed in last year, is D0 exponential minus EA by Kb into T. This is the Arrhenius equation. Now finally we have F3, which is the reaction step, and hence it will be given as Ks into Ci, where Ks is the rate constant for the conversion of silicon to SiO2. So now we have the equations for F1, F2 and F3. And in steady state, we can say that F1 is equal to F2 is equal to F3. And once we equate these, we can find the value of Ci and C0. So this is the basic case when it comes to oxidation in case of silicon. So I don't think they will be asking any descriptive kind of questions to solve for these three fluxes. You might be asked certain problems, maybe that is the maximum. This equation part or the derivation part is just for your understanding. Other than that, I don't think they'll be asking in-depth questions when it comes to the derivation. So F1, F2 and F3 and their equations, is it clear till now? So once we have these F1, F2 and F3, we'll have like the general solutions. I'm not going to the derivation of that part. The general solution can be written as D0 square plus A D0 is equal to D into T plus tau, where A, D and tau are basically constants, where A is given by 2D to 1 by Ks plus 1 by H. D is equal to 2dc star by n1, and tau is equal to di square plus a di by b. So can anybody just go through your notes and tell me what Ks, H, Ni, etc. are? Can anybody please try? What these constants are? Suppose they are asking you to solve a problem, you need to know what these constants are, right? Okay. Then what is H? H is the mass transfer coefficient and it is related to the mass transfer coefficient in gas phase by Henry's law as I mentioned, right? B again is a constant and here Ni is the number of oxide molecules that is incorporated in the oxide layer. So these are the constants that are there in A, B and tau. So is that clear till now? Like the in-depth explanation of how we arrived at the equation d0 square plus ad0 is equal to b into t plus tau is not required. So first thing you need to know is that there will be three fluxes that will be associated, and once you know the three fluxes, you will be able to get a generalized equation. The generalized equation is equal to d0 square plus ad0 is equal to b into t plus tau. So one another thing we can do is that we can rewrite this particular equation. So this the equation can be rewritten in the form d0 by a by 2 is equal to 1 plus t plus tau by a square by 4b the whole power 1 by 2 minus 1. So this is one important part. Basically, this same equation will be rewritten in this form. So the rewritten form will be d0 by a by 2 is equal to 1 plus t plus tau by a square by 4b the whole power half minus 1. So now we have already discussed, right? When it comes to oxidation, there are two types of limiting steps. One will be diffusion limited and one will be the reaction limited step. So this equation we will solve basing those assumptions. So we have to memorize this equation, that is d0 a by 2 plus is equal to 1 plus t by 2 a square by 4b the whole power half minus 1. So now we have two steps. So first one is the diffusion limited case. So can anybody tell me diffusion limited was in terms of thick oxides or thin oxides? Yeah. So when it comes to thick oxide, we have to take two assumptions. One is that T is very, very greater than tau. Also, T is very, very greater than A square by 4T. And hence this particular equation, right? D0 by A by 2 is equal to 1 plus T plus tau by A square by 4B the whole power half minus 1. So these are two assumptions. This is the first assumption, this is the second assumption, and taking these two into consideration, basically this equation will be reduced to D0 square is equal to B into T. That is the case in, and that is the equation in case of diffusion limited cases. So this is a parabolic rate law. Parabolic rate law. So we'll write y is equal to x square in case of parabolic rate law, which predicts that what will be the prediction if it's a parabolic rate law? The oxide thickness increases, the time increases as the square of thickness. So the rate constant V as a function of temperature is also given in your summary, right? So basically this is the case when it comes to diffusion limited reaction. So D0 square is equal to BT. So next we have reaction control case. So in case of reaction control case, the assumption is that T plus tau is very, very less than A square by 4B. Then this particular equation will reduce to what? D0 is equal to B by A into T plus tau. So this is the case when it comes to reaction control case. And reaction control case means that it will be a thin oxide. And so this is a parabolic rate law, right? D0 square is equal to B into T. This is the linear rate law. So thickness increases linearly with time. So this is how oxidation progresses in silicon that was discussed in terms of three flux. First we found out the equation for F1, F2 and F3. Then we equated F1, F2 and F3 assuming that it was under steady state and no dissociation was taking place. And using that we could find the values of C0 and Ci, which is the concentration of the oxidizing species at the two interfaces. And a generalized equation could be found out. So the generalized equation was D0 square is equal plus A D0 is equal to B into T plus tau, out of which A, D and tau were constants. So A is equal to 2D into 1 plus Ks by 1 by H, where 1 by H is the mass transfer coefficient, Ks is the rate constant, and Ni is the number of oxidizing molecules in the oxide state. And we have this equation. This can be rewritten in the form of D0 by A by 2 is equal to 1 plus T plus tau by A square by 4B the whole power half minus 1. So in case of thin oxides and thick oxides, we have two rate limiting cases. One is diffusion limited in case of thick oxide, and it is reaction limited in case of thin oxide. So whenever it is diffusion limited, we have two assumptions, that is T is very, very greater than tau and T is very, very greater than A square by 4B. So the equation will be condensed to D0 square is equal to B into T, which is a parabolic rate law. And in the reaction control case, the assumption is that T plus tau is very, very less than A square by 4B. Then the equation will be reduced to D0 is equal to B by A into T plus tau, which is a linear rate law. This is the oxidation step when it comes to thick oxides and thin oxides. So is that clear for all of you? So from the examination point of view, I think most important will be understanding what the three fluxes are. F1, F2 and F3. F1 means that oxidizing species coming from the gaseous phase to the surface, then diffusion through the oxide layer, and finally reaction between the existing oxide and the bulk silicon. That is F1, F2 and F3. So I hope this is clear for all of you. Yeah. So F1 is basically based on Henry's law. F2 is diffusion governance. Yeah. And third one is reaction governance. This is the reaction government, diffusion government, and here we have the Henry's law government. Is that clear? Okay. So, and one more question was regarding the salt exam, right? So let me take the salt example. So basically, whenever we are dotting from a solid source, what will be the equation? Can anybody remember and tell me? Okay, I think I have to do with it. So Cx of t will be equal to, now does anybody remember? So whenever we are doping from a solid source, the concentration at a depth of x and a time t will be given by qt by root of pi dt exponential minus x square by 4 dt. So this is basically a Gaussian function. And here Qt is the total amount of dopants on the surface at the start of diffusion per unit area. So that is also one thing you have to remember. It is the total amount of dopants on the surface at the start of diffusion per unit area. So this equation you remember, right? Cx of t is equal to qt by root of pi dt exponential minus x square by 4 dt. So once you know that, the change in concentration for a function of time can be obtained using this equation. So when x is equal to 0, it means that it is at the surface, right? So x is equal to 0 comma t. So this particular x will become 0 and this entire term will be 1. So it will be qt by root of pi dt. So these are two equations you need to remember. And once you know that, we'll go on to our example. So the example is that we have an n-type silicon wafer. So n-type means that it is having an n-type dopant. Here we are assuming it has arsenic, and Nd or the n-type dopant concentration is equal to 10 power 16 cm power minus 3. And now we need to form a PN junction. PN junction. And we need to understand at what depth the PN junction has been formed. And this P-type is induced into the material using a boron source. So initially our silicon wafer was N-type. It had Nd is equal to 10 power 16 centimeter power minus 3, and now we need to form a PN junction. Boron was used for doping. And the PN junction was finally formed, and we need to understand at what depth the PN junction was formed. We are assuming that the diffusion was carried out at a temperature of 1000 Kelvin. So basically, the diffusion coefficient for this boron, we can say D0 for boron is given by 0.76 and EA is given by 3.46. Now, can we find out D is equal to D0 E is exponential of minus EA by KB into T. So can you please substitute and tell me the answer? Sorry. Number of n-type dopants that are present in the material. So if it is n-type means that it will be electrons, right? Yeah. That is the dopant concentration. So initially we had a silicon wafer. We added arsenic into that and it became n-type. So that arsenic concentration is our Nd. And now we are again adding boron to create the PN junction. Is that clear? Yeah. So now can you please calculate D value for me? Like D0 is given to you, EA is also given to you. Sorry, how much? Okay. 2.87 into 10 to the power minus 8. Yeah. Now we have the D value. Right. So assuming that Qt is given to us and the value of Qt is 10 power 13 atoms per centimeter square. And the time taken for the PN junction formation is 2 hours. You have to convert this into seconds, right? So now on substituting all this, can anybody give me the x value using this equation? This equation. Like qt is given to you, you calculated d, t is 2 hours, you have to convert them into seconds, and finally you have to find out the x value. So in order for that, you need to know what is cx of t, right? Is it clear till this much? Yeah. Yes, exactly. So what would be cx of t? What you said is correct. So you're assuming that wherever n becomes equal to p, that is where your junction is formed. So cx of t will be replaced by 10 power 16. Right. Hello. Yeah. So is that clear? So basically, whenever we are asked such a question, PT will be given to you and time will be given, and you will be asked to find either the time taken or the depth at which the junction has been formed. Here the assumption is that initially we had an N-type wafer that is obtained by doping arsenic into the wafer, and the amount of arsenic atoms is given to you. And when the PN junction is formed, it is assumed that Nd will be equal to Na. That is, the number of P dopants will be equal to the number of N dopants. So Cx of T will be replaced by 10 power 16, and Qt is given to you. Time was also given. D you can calculate using D0 e raised to minus Ea by Kb into T. And once you have all the other values, the unknown x can be calculated. That is how we got 8 nanometers, right? 8.3, is it? Have you got what I meant? Is it clear to all of you? Basically, this is the step. Like Cx of T, we are equating to Nd. The reason is that concentration of P dopants will be equal to concentration of N dopants at the junction. So that is all. I hope it's clear to all of you. Is it? Yeah. Okay, so now I think we can move on to this week's content. So let me unpresent my screen. So is my screen visible to all of you? Is my screen visible to all of you now? Hello? Okay, so in the third week of fundamentals of electronic device fabrication, you had gone through what was etching and deposition. Then you went on to see IC device overview, etc. So first we'll start with etching and deposition, right? So the etching, in what is meant by etching? Can anybody tell me as a recap? In simple terms, what is etching? It's a very direct question. Yeah, basically it means the removal of material from the wafer surface, and it is combined with lithography so that we can selectively remove certain places on the wafer. Right. So there are two types of etching mainly. One is wet etching and one is dry etching. So can anybody tell me what is the difference between wet etching and dry etching? Okay. So wet etching, basically the wafers will be immersed in the tank of etchant, and there will be a chemical reaction happening between the wafer surface and the etchants, and hence material removal will take place. On the other hand, dry etching will be a rather controlled process, and there won't be immersion of the wafer onto the etchant. So it is the basically the removal of material in the absence of a solvent. Right. So there are some limitations. So why do we require dry etching? So basically there were some limitations that were associated with wet etching, that is incomplete etch, then over etching and under etching. So can anybody tell me what is incomplete etch and what would be the reason for an incomplete etch? Yeah. One thing is when we are not allowing for sufficient time for the etching process to take place. Another is when the concentration of the etchant is not sufficient, or when the temperature is not sufficient. And another defects associated with wet etching include over etching and under etching. Over etching means that part of the photoresist will also be stripped. That is when we are allowing for too much etching time. And under etching means that all the places are not evenly etched. As a result, what would be the reason we are not allowing for sufficient time, concentration, or temperature to take place? So these were the issues that were associated with wet etching. So we can say that wet etching is a rather difficult process to control. So controlling the dimension of this process was rather difficult. That is why we went on to dry etching. Right. And wet etching will be usually used for large pattern sizes that are greater than 2 microns. For smaller and much intricate features, we will be usually using dry etching. So wet etching, can anybody tell me, is it an anisotropic process or an isotropic process? Yeah, usually it will be isotropic. It can be anisotropic or isotropic, but in most cases it will be isotropic. And what happens is that whenever isotropic etching will be taking place, curved sidewalls will be formed. It is difficult to create intricate structures, and in case of dry etching, there is no such limitation. Right. And these are certain materials and the common etchants as well as the temperature that was used for this process. So different types of plant, dry etching, can anybody tell me? There were different types of dry etching, mainly three. So wet etching will be immersing in the solvent. Dry etching does not involve the use of any reactive solvents or immersion process. So basically there are three types of dry etching. Can anybody memorize and tell me if you have notes or so? Yeah. Plasma etching, ion beam milling, and reactive ion etching. So in basically in plasma etching, the chemical etchant will be introduced in the gaseous phase. For example, for silicon oxide, tetrafluoromethane will be introduced into the chamber, and once the chamber is evacuated, first we will introduce the gas, and plasma will be introduced, and this ionizes the gas. Then the ionized gas will be used for attacking the oxide layer and removing the material. That is the plasma etching. Now we have ion beam etching. It is similar to the ion beam milling process. We know ion beam milling process in transmission electron microscopy, right? Similarly, we have an ion beam etching. Here an ion like will be used for removing the material from the wafer. This process is not selective, but the advantage is that ion beam etching is highly directional in nature. And then we have reactive ion etching. Reactive ion etching basically combines the plasma etching and the ion beam etching process for both selectivity as well as directionality. So that are the three types of dry etching. So the thing is that dry etching rates are much slower in comparison to wet etching, but we have better dimensional control. That is why when we are going for very nanoscale features, we will be preferring dry etching over wet etching. So these are the two types of etching. So here we have plasma etching figure and ion beam etching. So plasma etching is chemical removal, ion beam is physical removal, reactive ion is both chemical and physical in nature. And so till that, is it clear? Yeah. So next we move on to deposition. So this first lecture was about etching as well as deposition. So in case of what is meant by deposition? Can anybody tell me? What is deposition? Yeah, basically it is the opposite of etching. Here material is added to the wafer surface, right? So deposited films are usually used when we want to create epitaxial layers, dielectric layers, when we want to create trenches, or in capacitor deposition for intermetal conducting flux are to be deposited, etc. So deposited layers are usually grown using either physical deposition or chemical deposition. So here we will be seeing chemical deposition in detail. So some important parameters that we need to keep in mind while depositing these material include the thickness and uniformity, roughness, how the composition is varied, whether stresses are introduced into the wafer, where contaminants are introduced or not. These are certain factors that we need to keep in mind. So first is chemical vapor deposition. So last class we had given, I had given a small overview. What is chemical vapor deposition? Can anybody remember and tell me what was difference between physical and chemical, or what you know about chemical vapor deposition? Both are deposition processes, physical vapor deposition and chemical vapor. So basically from the name itself you will get an understanding. Physical vapor deposition and chemical vapor deposition. Like, just give me your thoughts on what you feel would be the difference. Anybody? Okay. So basic principle of chemical vapor deposition is that chemicals containing the desired film or layer will be introduced into the reactor where the wafer will be held at a very high temperature. And so this depositing layer will be introduced into the reactor and it will be in the form of a wafer. And then this vapor will react onto the wafer surface to form a thin film. That is how the material will be deposited. So whatever material we want to add onto the layer of our wafer, it will be introduced into the form of a gas. In the gaseous state, it will be introduced into a reactor at a very high temperature. Then these gaseous wafers will go and adhere themselves onto the surface of our substrate, and a chemical reaction will take place and a thin layer will be formed. That is how chemical vapor deposition is carried out. There are many examples like pyrolysis process, reduction, oxidation, nitridation, etc. These are all chemical reaction where a new layer will be deposited onto the surface of our wafer. So another method where we can grow atomically thin films layer by layer is atomic layer deposition. That is also yet another type of deposition process. Is that clear? Chemical vapor deposition. Yeah. Then we have chemical vapor deposit. Along with that, we have ALD. Then we have molecular beam epitaxy. Molecular beam epitaxy, it is used for low deposition temperature and highly rate controlled processes. So basically, a chamber will be there, and in the chamber will be having the materials that are to be deposited on the surface. Those, am I audible to all of you? Yeah. So these materials will be taken in their pure form in what are known as effusion cells. If you see these small triangular features, these are known as effusion cells. Then they will be evaporated and then they will be directed onto the substrate. That is how molecular beam epitaxy is carried out. They are evaporated and then deposited on the substrate. So molecular beams will be used for forming the film. That is why this is known as molecular beam epitaxy. And it is a highly controlled process. We can control the amount of dopants that are deposited and also the number of atoms that are actually converted. So I hope that is clear. That is etching and deposition. That was the first lecture. So now we'll move on to the next. Next is metallization. Can anybody tell me what is metallization? What is the process of metallization? So basically, what do you understand by metallization? Yeah. Basically, once the wafer is formed and a circuit is complete, we need wiring. We need a circuit to allow the electricity or the conductivity to pass through, right? So that process, metallization, basically refers to wiring various components together to get a functioning circuit. That is the metallization process. So as the name suggested and as you said, basically we are depositing metal layers onto the surface of our wafer or in between our layers. So basically, integrated circuit fabrication, it will be divided into two parts, FEOL and BEOL. So FEOL basically means front end of the line. It means FEOL basically means that it involves the fabrication of the active and passive elements of the circuit. Metallization actually is part of back end of the line. Metallization, so these are metallic layers that are used to make interconnection between these various active and passive components that are manufactured in FEOL, and then it will be then finally connected to the external devices. So that is the metallization process. So variety of techniques are used for depositing metal layers in an IC. So this includes sputtering, chemical vapor deposition, electroplating, etc. So sputtering is a physical vapor deposition process and it is used for aluminium and aluminium copper alloys, etc. Chemical vapor deposition is used for polysilicon and tungsten, etc. Electroplating is usually used for copper deposition. So these are the three metals that are usually used in providing these wiring or electrical contacts between the different active and passive components. So one thing to remember is that in FAOL or front end of the line, we will be manufacturing the active and passive components, and in back end of the line, we will be providing electrical conduits between these layers. So that is where metallization comes into picture. So as I already mentioned, it can be done using sputtering, chemical vapor deposition or electroplating. So these are basically like it's giving us images on where like various physical vapor deposition techniques like thermal evaporation, electron beam evaporation, sputter deposition. So next is planarization. So can anybody tell me what is planarization? Yeah, so far you have made the electrical circuit, you have provided electrical contracts using metallization. Now we are doing planarization. What is planarization and why is it required in lithography? Yeah, basically it means achieving surface roughness means that it is used for achieving a flat profile on the wafer surface. So why is it important? So basically, yeah, exactly. So planarization is required because whenever this mask is aligned with the wafer, we require proper alignment and there should not be any residual roughness. And also to get exact focusing of this ICs, we require planarization. So basically, if you Google, you'll be able to get the image of a non-polarized IC with a planarized IC. So in case of a non-planarized IC, aligning the masks or producing the connects will be very difficult and this will induce defects. So chemical mechanical polishing is usually used for achieving the global planarization over the entire wafer. Right. Basically, in planarization, the wafer will be mounted onto a rotating stage or rotating platen. Then it will be polished using a polishing plat, and slurry will be introduced, and this slurry will be having certain abrasive particles. So the abrasive particles will rub against the wafer surface, and it will remove the small roughness features. And the polishing pad and plating will rotate in opposite direction so that the slurry can remove the small particles instead of being stuck. So this is how the polishing process is carried out. So is that clear? Yeah. So, so there are two terms that are associated when we are coming to metallization and planarization. So trench is basically electrical connections within the same layer, and via is the electrical connection between different layers. So is that clear? Yeah. So one another process that we need to remember is the somebody has messaged something. Okay, Vinay Kamath has raised a hand. Okay, like you want the image. Okay, let me see if I have an image of that. Okay. Here I think it's not visible. So, okay. So this image you can see, right? And in this image, if you see, you have first layer, second layer, third layer, like multiple layers are there. And in these layers, they need connection not only within the same layer, they need connection within the same layer and across different layers, right? Okay, and for producing such contacts, we will do metallization. Different components will be there in a single layer, and one component has to be connected to another component within the same layer, and one component in this layer has to be connected to another component in another layer. That also is required. Okay, so when electrical connections are within the same layer, it will be called a trench, and when it is between different layers, it will be called a via. Yeah, and these layers will be stacked one like for us when we see the image we'll feel that these are very thick structures, but usually there will be multiple layers and they will be stacked over one another, and overall the entire thing will only be in micron layer thickness. So it will be very thin layers that are stacked one onto the other. Trench basically, as I mentioned last time, something basic trench is a term that is used for something that has a very high aspect ratio. That is something that is very deep. Like one of the dimension will be very large compared to the other dimension. Yeah. It will depend upon the type of component that you are like using, like whether it is a capacitor or a resistor. It will be a combination of many of these things, right? Yeah. So next is the copper dual Damascene process. So basically it is used in copper metallization process, and copper is usually a replacement for aluminum copper alloys. Copper has a lower resistivity and lower electron migration effect as compared to aluminum. So that is where we use the dual Damascene process. Does anybody remember from the lecture what the dual Damascene process is? Okay. It is used for copper metallization. It is basically a lithography process, right? Yeah, so basically it's a lithography process, and what we will do, a low K dielectric or a barrier layer will be deposited and separating metal layers, then copper electroplating will be carried out, and finally chemical polishing of the metal will be carried out. So the dielectric layer is first deposited. In case of organic low K dielectrics, it will be spun on or patterned. And for oxide layer, CVD will be used for deposition, though it is harder to integrate with conventional lithography. Then the metal layer will be deposited by electroplating. A barrier layer is first deposited, followed by a seed layer. Then electroplating will be used for depositing rest of the metal. And finally, polishing will be used for removing the excess metal and achieve a planar surface. And the process will be repeated for multiple layers. Basically, it is a copper metallization process. And if possible, frequency, first the intrinsic dielectric layer will be filled, then the metal fill, and finally excess material will be removed by chemical metal polishing. That is basically the dual Damascene process. It is used for copper metallization. So next final lecture on this week was about process control. That is IC process control, where electrical measurements etc. were made. Right. So we'll start with that. Process and device evaluation. So why do we require process and device evaluation? So can anybody give me some general answers as to why we require IC process control? Like why do we need IC process control and what is IC process control basically? Yeah. So basically, integrated circuit manufacturing, it's like an assembly line process, and there will be more like hundreds of steps involved, and like before we get the final article, right? So basically, process or device evaluation is critical because we need to ensure that all the chips or dies or every component is working correctly after each step without significantly altering the total process cost and time. This is because once we wait to evaluate the component after the final stage, and if it is found out to be not working, then a lot of time and money involved in the process will be lost. Therefore, after each critical manufacture, we will be using certain measurements to make sure that these components are working correctly. So that is why we require process or device evaluation or process control steps. Is that correct? Yeah. So this process monitoring can be done directly on the process wafer, or we can separately manufacture test wafers and that will be processed along with the product. So there will be specific test wafers that are manufactured, or we can do it on blank wafers just to monitor whether the particular process is working or not. And we will be usually doing electrical testing, physical parameter measurement, and defect measurement. Electrical testing to make sure that the component is correctly conducting and it is functioning in its requirement. Next is physical parameter measurements, whether its dimensions are within the required limit or not. And finally, defect measurements, whether when we were doing heat treatment or when we were doing polishing, etc., whether some physical defects or some stress or strain was induced into this particular wafer. So electrical measurement. Electrical measurement, can anyone tell me how electrical measurements would be usually carried out? So it's basically measuring one thing in the material. So what would be that thing? Like we can understand the entire electrical properties by measuring a simple thing. What would be that? So in electrical measurements, the first and foremost thing that we will be measuring will be anybody? Take a wild guess. So I told whenever we are doing process control, first we will have to do electrical testing, then we will have to do physical parameter measurement, and finally defect measurement. When it comes to electrical measurement in terms of IC, the first and foremost thing that we will test will be what? Yes. So basically, electrical measurements usually in case of IC measures refers to the measurement of resistance in the component. And why do we measure resistivity whenever we are like manufacturing a wafer, adding dopants, or when we are removing dopants, or we are doing layering process, etc.? All of this will affect the resistivity of the material. Resistivity will in turn affect our conductivity. Is that right? Yeah, and once we get the IV characteristics, when we can go on to further classify the electrical measurements. So basically the first thing that we will be doing is that we will do resistivity measurement. So here this is the equation for resistivity. Rho is equal to pi t by L into V by I. And using these IV characteristics, then we can go on for further measurements. So the basic thing when it comes to electrical measurement is resistivity. Is that clear? Yeah. Okay, and next is physical parameter measurements. Physical parameter measurements means that we need to make sure that whatever we have manufactured, its dimensions will fall within a particular limit. And for this physical measurements, we will be using certain techniques like white light interferometry, spectrophotometers, ellipsometry, profilometry, etc. So, can anybody tell me what is white light interferometry? Like from the name itself, we can say that it will be related to interference, right? Yes. So basically it is used for measurement of thickness of the film, and due to the interference of light that is reflected from the top and bottom of the film, there will be a color code, and based on this color code we will be able to understand what would the thickness value lie in between. The exact thickness we might not be obtaining, but the range of thickness would be obtained, and from this particular range we will be able to understand whether it will fall in between our limits or not. Similarly, we can use spectrophotometer. People's joining. Next, we have spectrophotometer. Spectrophotometer also uses constructive and diffractive interference in order to form fringes like the ones we have in XRD. And based on this, we will be able to get the thickness. Another thing we can use for physical measurement is non-contact or contact profilometry. That also uses, like, it's a measuring technique for surface topography. Either we can use a light source or we can use a touching probe that can be used for measuring the thickness of the layer or the component that we have manufactured. Ellipsometry is also another widely used technique, and that is based on polarization of light when it is reflected or transmitted through a medium. So these are basically ellipsometry, profilometry, spectrophotometer, and white light interferometry, etc. are techniques that are used for thickness measurements. So I think, yeah. And finally, we have contamination and defect detection. Can anybody tell me how to find out contamination and defects in terms of IC evaluation? How do we do defect detection? So basically, defect detection in terms of IC can be done using scanning electron microscope or transmission electron microscope. And if the features are very large, it can be done using an optical microscope as well. If we are using a scanning electron microscope, we will be able to get at the surface morphology of the layer that we have deposited, and the surface defect density, defect size, composition, etc. can be found out. If we are using a transmission electron microscope, we will be able to get defects at further, like in-depth defects. The bulk characterization can be carried out, and we will be able to see features at a much larger resolution. So that is what is there in IC process control. Basically, whenever we are manufacturing an IC, it is required that we need to inspect the components that we have manufactured at each stage, so that we will be saving time and money. And this character or this process control basically is into three types. One is electrical measurements, then physical measurements, and finally defect characterization. Electrical measurements, first and foremost thing we will be studying will be the resistivity. Once that is done, we can go for IC characterization, IV characterizations. Next, when it comes to physical measurements, that is usually for finding out whether the dimensions are appropriate or not. For this process, we will be using white light interferometry, ellipsometry, profilometry, etc. And finally, for defect characterization, we will be using techniques like optical microscope, scanning electron microscope, and transmission electron microscope. So is that clear till now? Yeah. So now, yeah. So now we have gone through the recap of the week. So we'll solve a few questions. This. Okay. Planarization refers to the process of A. Orienting the crystal planes on a wafer surface, achieving a flat profile on the wafer surface, slicing the wafer along the crystallographic planes, and depositing thin sheets of conductive material on the wafer surface. So, what is planarization? And you have to tell me what is planarization and why planarization is required. I've already mentioned when we went through the summary. Yeah, achieving a flat profile of the wafer surface. So, why do you need planarization? Yeah, so that whenever we are doing alignment, there should be no misalignment when it comes to arranging the layers one on top of the other, and this should not lead to lesser focus, right? So that is why we require a flat profile on the wafer surface. So a common etchant that is used to remove silicon nitride is dash. If you like, and if you have either you can Google, or if you have the summary PDF with you, that it used to have a table. In that table, it will be there. It's not KOH, then that was SiO2. This is silicon nitride. KOH, I think, is for SiO2. This is H3PO, phosphoric acid. That is usually used for removing silicon nitride. So, silicon nitride is commonly used as a hard mask instead of silicon oxide when etching silicon using KOH. Which of the following is a valid reason for this choice? Silicon nitride is easier to deposit than silicon oxide. Silicon nitride layer has less stress than silicon oxide of same thickness. Silicon nitride etches much slowly in KOH than silicon oxide. Yeah, can you give an explanation? Like how you arrived at the answer C? Like everybody can try, even if the answer is wrong, it doesn't matter. You can give your idea of why C would be an answer. Anybody can contribute. And feel free to talk. Yeah. So basically the thing asked here is that silicon nitride is commonly used as a hard mask instead of silicon oxide when etching silicon using KOH. So basically we have a silicon substrate, and on top of that we will usually use silicon nitride. We won't use silicon oxide. What would be a reason? This is because whenever we are using KOH, the KOH has to like consume the silicon, but it should not affect the silicon nitride, the mask layer, right? So then what it should be, silicon nitride, the etching rate of silicon nitride should be much slow in comparison to silicon oxide. So is that clear? It should consume the silicon, but it should not consume the hard mask. So in comparison to silicon, silicon nitride will be having a very slow rate of being consumed. Is that clear? Yeah. So basically you can read this explanation. Etching process should be selective to the material that has to be removed to protect the material under the mask as well as the mask material itself. The etch rate for silicon that is 100 at 90 degrees Celsius using 30% K, which is 100 micrometers per hour. If silicon nitride is used, its H rate under the same condition is 1 nanometer per hour, nearly 10 power times lower than that of silicon. On the other hand, silicon dioxide, the H rate is approximately 1 micron. So using silicon oxide will not be good enough, or a very thick oxide layer will then be required. Thus silicon nitride will be used. This is because for every 100 microns of silicon that is eaten, only 1 nanometer of silicon nitride will be eaten away. But if you are using silicon oxide on the other hand, for every 100 micron, 1 micron will be eaten away. That is much higher, right? So after a certain amount of time, the mask itself will erode away. So that is why we will be using silicon nitride instead of silicon oxide. So is that clear? Yeah. So which of the following is a valid comparison between dry and wet etching? Etching rate in wet etching are typically lower than dry etching. Dry etching tends to produce better dimension control. Dry etching is anisotropic while wet etching is always isotropic. Dry etching is only a physical removal process while wet etching is only a chemical removal process. A valid comparison. There will be some extent of truth in some of them, but which would be a valid comparison? Yeah. So the answer will be B. Dry etching tends to produce better dimension control than wet etching. So see, if you see, it is a generalized statement, but wet etching is not always isotropic. There are certain cases when it is anisotropic in nature. So it is not a generalized statement. But if you are looking at D, dry etching tends to produce better dimension control in all cases than wet etching. So etch rates for wet etching are typically higher than those for dry etching. Wet etching is used for removing material from larger areas, and for smaller areas and precise etching, dry etching is generally preferred. It tends to produce better dimension control than wet etching. Okay. Which of the following semiconductors are normally deposited by molecular beam epitaxy? Silicon, germanium, gallium arsenide, and zinc oxide. Yeah. And the reason? Okay. So basically, gallium arsenide is deposited by molecular beam epitaxy. The source materials are pure Ga and Gas, which are evaporated from the effusion cells. So can everybody take a few moments to find out why gallium arsenide is usually deposited by molecular beam epitaxy? You can either go through your notes, or you can go source and use other sources like Google and find out why usually MBE is done using gallium arsenide. Yeah. Any other answers? Okay. So I want you guys to find out for next week. I will be asking which of why gallium arsenide is usually deposited using MPE. So can everybody find out, and some of you guys can give me an answer next week, I hope. Okay. So we'll move on. Okay. In BEOL, that is back end of the line, copper is deposited in order to make electrical contacts. Which of the following techniques is not used for copper deposition? Electroplating, sputtering, thermal evaporation, and CVD. Any other answers? Sorry? Okay, one person told sputtering, one person told thermal evaporation, others? So the answer is basically CVD. Electroplating, sputtering, and thermal evaporations are usually used for depositing copper to make electrical contacts. Chemical vapor deposition is mainly used to deposit polysilicon and tungsten, and for depositing barrier layers, that is silicides and nitrides between silicon and copper. So I think it was there like what all processes are used for which all materials are there in the lecture. If you go through the lecture, I think you'll be able to answer it. Okay. So next is the layer that is used for providing electrical connection between two horizontal layers of interconnects is, it's not ILD, it's either between trench or wire. So if you remember, between this in between same layer, no, between two horizontal layers. Sorry, no, wire. Not material, different layers. Yeah, basically you have one layer, second layer, the layer that is used to provide electrical contact between two horizontal layers. Two horizontal layers between means two different layers. Between the same layer means it would have been trench. Since it is two horizontal layers, it is wire. Yeah. So trenches are used for making electrical connections between metals in the same layer. Wires are used for providing electrical connection between different metal layers. ILD refers to interlayer dielectrics, which are used for separating various metal layers in multi-layer metallization. Okay. Next is so problem. Okay. Silicon wafer of thickness 500 microns has to be etched to create silicon nitride cantilever. If KOH is used as the etchant at 90 degrees Celsius, what is the approximate total time for this process? Give your answer in hours. Given that the etch rate of KOH at this temperature is approximately 35 nanometers per second. So we have a silicon wafer. We have to make an SiN cantilever, and KOH is, yeah. Basically cantilever, let me draw something that has an extension. Suppose this is one line and we are creating a dimension like this, a T-shaped structure, something that has support only on one side. Suppose in the wafer we are creating a structure, suppose we want an electrical contact that is in a T shape, that is the cantilever. Yeah, we can say that is cantilever. Yeah, like it will be having an attachment only on one side, the other end will be free. That is basically a cantilever. Can people start solving? So in the meantime, let me see if I can find the image of cantilever. Suppose in your circuit somewhere you have something like this. Like one part will be attached, one end will be free. That is a cantilever. Is that clear? So now can you people solve and tell me the answer? Silicon wafer thickness is given to you and the etch rate is also given. So basically you have the wafer thickness and that wafer thickness has to be reduced, right, into another structure. And the rate at which it will be eaten is given to you, 35 nanometers per second. Okay, yes, the answer is 4 hours. Basically, this entire wafer thickness you will have to divide it using the H rate. And both of it will have to be converted into the standard SI units. So microns and nanometer both were converted, and finally we got the value in seconds, and then by dividing into 3600 we got 4 hours, 3.97 hours. That's approximately 4 hours. So is it clear for all of you? Basically, you had an entire wafer. That entire wafer will be eaten in so and so rate. So if you're dividing the two, we will be getting the time taken, right? Even from the units, you will be able to understand. So this is basically thickness alone. This is thickness per second. Suppose you're dividing, you will be getting S inverse will be going into the numerator, and we'll get the time taken. That can justify your logic. So is that clear? So next is the resistivity of a thin film sample measured by 4-probe technique is given, where T is the thickness of the film. Consider a 50 nanometer thick platinum thin film. The resistivity is given as 106 nanomohms meter. If the current through the probe is 10 microamps, milliamps, what is the approximate voltage difference? Give your answer in millivolts. Basically, resistivity is given, thickness is given, resistivity, thickness, current, what is the voltage? We have to find out V. It's basic substitution. Somebody posted something. Ma'am, can I get the notes for reference? Yeah, these PDFs I will be uploading in the Drive link, and that will be given to you. Sure. And whenever you're feeling that you're not able to understand the classes, transcripts will be uploaded. So those, if you read those transcripts, you'll be able to see what the lecturer was exactly saying during the class. So if you compare that with your notes, you might be able to get a better understanding. Instead of viewing the lectures again and again, you can go through the transcripts. That's one another thing that you can do for a quick revision if you want. Has anybody got the answer? The only thing is that everything should be converted into the same units. Other than that, it's a direct substitution. Have you got? Has anybody got? 106 you have to substitute 106 into 10 power minus 9. Then 50 nanometer 50 into 10 power minus 9. Current through the box you have to substitute as 10 into 10 power minus 3. So rho is given, that is the resistivity. B you have to find out. I is the current through the box. T is the thickness, which is 50. That is 50 into 10 power minus 9. When you substitute all of this, you'll get a value into 10 power minus 3. So that if you see, if you convert into millivolt, you will get as anybody got the answer? Hello, am I audible? Everything you have to convert to SI, rearrange the equation. B you have to find out. Has anybody got the answer? Where are you finding difficulty? Like where it's going wrong, can you let me know? Shall I display the answer or shall I wait for some minutes more? Yeah. So basically, like V you have to rewrite as rho into I ln 2 by pi t. This rho is 106 into 10 power minus 9. I is 10 into 10 power minus 3. Ln 2 you substitute as it is. Pi you substitute as it is. This was 50 nanometers. So 50 into 10 power minus 9. Basically you get 4.675 so on and so on into 10 power minus 3. So that 10 power minus 3 we are taking here as milli. So finally you get 4.7 millivolt. Is that clear? Yeah, so where did what was the mix-up? Can I get to know it? What was the issue? It's a direct substitution. Yeah, and I suggest that while you're practicing, try to download the online calculator and practice so that you speed up your calculations on those. Because in the examination, an online calculator will be provided and you'll probably have to use them. So, a bright fringe is seen in a spectrophotometer when the path difference is an odd integral multiple, even integral multiple, an odd integral multiple of half wavelength, and odd integral multiple of even integral multiple of half wavelength. Basically, it's a diffraction question. Somebody has unmuted. Odd or even. So we are asking constructive interference. Bright fringe happens when constructive interference happens, right? So what will be the condition for constructive interference? Will it be an odd integral multiple of half wavelength or even integral multiple of half wavelength for constructive? Yeah, it will be the even integral. So in basic physics, you might have known terms like constructive interference and destructive and destructive interference. And so when the path difference is an odd integral multiple of lambda by 2, always there will be a dark fringe. And whenever the path difference is an even integral multiple of half a fringe, that is lambda by 2, we will be having constructive interference. And whenever we have constructive interference, we will be able to see a bright fringe. So spectrophotometer is basically based on the principle of interference. A monochromatic light source will be used and we will be getting fringes due to interference. So if the thickness of the film is d and the path difference between the light reflected from the top and bottom is given by 2m into lambda by 2. Usually we write 2m or 2n where n is the order of reflection. A 2n into lambda by 2 is constructive interference. 2n plus 1 into lambda by 2. That is something it is odd into lambda by 2. It is destructive interference. So constructive interference is what takes place for integral multiples of half length. That is even integral multiple and a bright fringe will be obtained. So that's the case. So if you see incident light is there and the path D is there. If you see this image, you might recall this will be the reflected wavelength and from the second plane it will be this one. And if the path difference between A and B, that is this line, this particular line, if the path difference is equal to 2m into lambda by 2, they will be constructively interfering, that they will be in phase and a bright fringe will be formed. Suppose that this distance or say any other nth distance will be 2n plus 1 into lambda by 2, their phases will not be in the same and hence they will destructively interfere or cancel out and finally we will be getting, now we won't be getting anything, we'll be getting a dark fringe. That is constructive and destructive interference. So is that clear for all of you? Yeah. So do you have any like from last class we had discussed about fluxes, do you have any doubt from this week's like content that I need to present next week? You can ask me. Like whether you want clarification on any particular topic or any area, we can spend a few like some time on that in the next week. So any particular doubts, etc. Anybody, any doubts from previous week? Like if you want any clarification on whether it is oxidation or doping or maybe what layering, IC process control, wet etching, dry etching, etc. Yeah, please, Chandrasekhar. Okay. Yeah, it's usually the high K dielectrics. I think it will be coming in the subsequent weeks. Yeah. Yeah. Okay, so maybe so should I like give a few minutes of class on difference between low K and high K dielectrics and where they are used next week? Will that be okay? Yeah, okay, sure. Yeah, that I can do. Anything else? Yeah, sure. There is a discussion forum in the Swayam portal. There also you can post your questions. Yeah, yeah. In case you get any doubts while going through the lecture or while reading or revising, etc., you can post there. Like there is another teaching assistant, so she will be answering there. So in case you want me to answer anything, you can post it to my mail ID. Yeah, sure. Santhra.pmrf@gmail. Santhra, SANTHRA dot PMRF at gmail.com. Yeah, I'll post in the chat box. Wait once again. Yeah. Yeah, there is a slight change. Santhra.pmrf@iatm at gmail.com. Nazia, there is a slight correction. Santhra.pmrf@iatm at gmail.com. Yeah, sure. Okay. Yeah. So either you can post in the discussion forum or you can mail to me. So either way, you will be able to get your queries clarified. I think most probably we'll be having only two more sessions. One is a final fourth week session, and before the examination, usually we will be having a rewind session, like overall solving a few questions and so on. So that's all. Yeah. Yeah. So thank you everyone for joining. Thank you so much, and wish you a great independence. Yeah. Sure. Yeah. Yeah. Okay. Okay. So I think, but even now you have two more assignments, right? Yeah, so two more assignments plus your final examination, you will get good enough marks to pass the examination. You might not be able to get full on full, but still for getting certified in this course, that will be enough, I think. Yeah. Okay. Have you registered for exam? Okay. So either thing is you can just, if you want to get certified and if that is fine for you, then you can go for examination this time. But if you feel that you need a very good score or something, I think you can drop a mail to the NPTL team. That is one thing, asking whether like, you can submit the assignments or some another thing is possible. Or one more thing is that you can join, like you can study the course now and write the examination up by registering in the next run. That is next August or September. Yeah, it will be repeated every year. Yeah. So, like just in case, since there are 3 days in hand, you can drop a mail to the NPTL. Like in Swayam portal, there will be a help desk mail. You can drop a mail there as well. Okay. Okay. So, okay, then probably you will have to go for the next run of the examination. But suppose you are doing another course or working in research environment, etc. Then I think this mark value as it is won't be that important. Okay. Marks value. Okay, then fine. You can go for the examination in the next run. Yeah, right. Yeah, yeah. Assignment. Yeah, 25. Like out of the all assignments, no. Like from all the assignment, 25% of those marks will be taken. I guess 25 or 50. No, 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 no. It can be MCQ as well as single line descriptives and so on. So that will depend upon the faculty who's setting the question. But usually, most of it will be MCQ. Yeah. Yeah. So I hope that is all for this week. So thank you everyone for joining. Wish you a great Independence Day. And thank you so much. Yeah. Yeah. Bye. Yeah. Thank you so much. Bye.